Hello and welcome back to Calculus 1, section 3.3, Rules of Differentiation. All right, so first, find the derivative of f of x equals to square root of 3x minus 1. All right, well, we know how to find the derivative, obviously. Limit as h goes to 0 of square root of 3 times x plus h minus 1 minus square root of 3x minus 1 divided by h. So all we need to do is to compute this real quick, and we're done. That's how we find the derivative. So let's see. We rationalize this. I'm just going to write this as 3x plus 3h minus 1 plus square root of 3x minus 1 divided by square root of, I'll leave this one. This is the experience of which ones you leave, which ones you distribute. So now equals to the limit. H goes to 0. The numerator becomes 3x plus 3h minus 1 minus 3x plus 1 when you distribute, divided by h times, in parentheses, square root of 3x plus h minus 1 plus square root of 3x minus 1. In the numerator, 3x, negative 1, and positive 1 all cancel. And then in a second wave, well, equals to here. Limit h goes to 0. What's left in the numerator is 3h. And in the denominator, we have this wonderful h times the parenthesis. So now, h cancels. And we can finally apply the h equals 0. So we have 3 divided by square root of 3x plus 0 minus 1 times plus the square root of 3x minus 1, which is, dare I say, clearly 2 square roots of 3x minus 1. This is the derivative. It's the function that will generate all of the slopes for tangent lines when you provide those x's. Now, obviously, if x is 1/3, the whole thing explodes. But anything else other than 1/3, it will generate a number. It will generate the tangent line. So what's a big deal, right? It's a big deal, because we can measure the change now. Look at this calculation. And this is a simple problem. How they're gonna, the other ones that are not as simple look like. So the rest of the chapter 3, from this section on, will teach us shortcut techniques. And every time when you even start thinking about something being complicated or annoying, understand that this would be orders of magnitude worse. So everything that we learn in chapter 3 is for our benefit, is a shortcut, is the simplest possible way that it can be put together. That's what the rest of the chapter 3 is. And if that seems complicated or crazy, as I said, this will be thousands and thousands of times worse. So we are not going to use this method ever again to compute the derivative in this class. We are going to learn now in 3.3 shortcuts. You are going to memorize stuff. You already dealt with that in your life once when someone told you memorize multiplication table, and you did. What's the alternative? 7 plus 7 is 14, plus 7 is 21, plus 7 is 28, plus 7 is 35, plus 7 is 42. Where someone said, oh yeah, 7 times 6 is 42, because they memorized it. So now you are going to memorize shortcuts. See, multiplication table is shortcut for repeated addition. You memorized from 1 times 1 to 10 times 10 a grid of 100 values. There are 100 combinations there. So to say 10 times 10 is 100 and start 1 times 1, right? That's 100, 10 by 10 grid. And you also know 0 times something. So actually, you, right, 0 times anything is 0. So, well, for now. So you have knowledge of 101, let's say, right? So now what we are going to memorize is the formula for the derivative of a polynomial, formula for derivative of sine, formula for derivative of cosine, formula for derivative of e to the x. And all of those are going to be memorized throughout the chapter 3 in various sections, where you will be allowed to actually skip on doing this. Your exam had a limit for sine. That thing was actually the proof for the derivative formula. Yes, it is 3 steps, right? But the trick is that why do even that? If you're just going to memorize the derivative of sine is cosine and you're done. That's it. There's no need to write 3 lines of this to get there every time you need it. And you need it all the time. So that's the trick. Take differential equations, you see. So what are these things that we must memorize? Well, we start with the one that you already know. I talked about it in the last section over and over again. The derivative of a constant is 0 because there is no change. That's the big one. What's the derivative of 7? What's the derivative of 107? What's the derivative of pi? 0. What's the derivative of 37 squared? 0. We don't care how much 37 squared is. It's going to be a number, and we don't care whether the number is small, negative, whatever. We don't care. It is, if it's a constant, the derivative is 0, and that's the end of the story. Next one. The derivative of any polynomial. Now, this is a powerful formula. I'm not saying x squared or x to the 5th. I'm saying all of them at once, all right? This formula will work no matter which exponent you provide. Give me square, it's x squared. Give me 5th, it's x to the 5th. But it can also be 1 over x squared if you give me negative 2. It could be cube root of x if your n is 1/3. This covers not just polynomials, but it covers rationals, it covers radicals as well. So depending on this n, it works across the board. So you can find the cube root of x, 100th root of x, or the derivative of x to 100, or 1 over x to 100. What is the formula that you're memorizing? You're memorizing nx to the n minus 1. It's the same n, right? So don't make it difficult, okay? If this is 8, then that's 8 and that's 7 eventually, right? If this thing over here is negative 1/2, because your problem was 1 over square root of x, then that's negative 1/2, and it's going to be negative 3/2. So I'm going to do examples, obviously, but it's that simple. If you try to do the alternative, well, good luck, right? Because you have to go and rationalize and enjoy everything you saw at the beginning of the class. Did I put the stream on? Yeah, good. All right. So, as examples here, start with good old x squared, right? Which would be 2 times x to the 2 minus 1, which is 2x, right? We know that one. The derivative of 1 over x cubed, for instance, is the same as asking about the derivative of x to the minus 3. If you know algebra. If you don't know algebra, then you should retake that first. So you drop n down as is, it's negative 3, and then just subtract 1 from it. Minus 3 minus 1 is minus 4. Fifth root of x to the 8th. You immediately rewrite that as x to the 8/5, and then you do the magic. So these problems should literally take 2 seconds. No intermediate steps necessary, right? If you can go from the first to the last, fine. There's no need, if you don't have to rewrite it to see it, if you see it through the algebra right away. If you need to rewrite, then rewrite. I'm just going to make this x larger. So that's that rule. So far we have these 2 rules, very important rules. Now, there are also some properties that I'm going to sneak in here and there. Here's one. If you are taking the derivative of a constant times the function, you can kick the constant out and just take the derivative of the function. It's a cool property. It's not a formula to find derivatives. This is something that helps you grind through the problem. So let's say you are looking for the derivative of 10x cubed. Well, by the property, you can kick 10 out and find the derivative of x cubed. So it's going to be 10 times 3x squared, which is 30x squared. Now, I understand that the next Saturday, you will be going from here directly there. Fine. All right? That's okay. But I just want to illustrate mathematically what are all the steps that are happening. So the coefficient in front of the function, the constant, can be kicked outside. So you are only focusing on taking the derivative of this part, which is the function. And then you will be multiplying that later. So that's that part of taking the derivatives. You kick the constants out. Another cool property is that if you have multiple functions added together, you get to differentiate each piece separately. Now that works only for addition and subtraction, doesn't work for multiplication and division. We'll have separate formulas in the next section, as some of you know, those who did class prep. So another property would be that the derivative of f of x plus minus g of x is the derivatives of each independent one, added or subtracted. Depends on what you started with. So that's another property. This allows us to grind through longer problems. So say you have x cubed plus 5x plus square root of x to the square root of x to the 7th minus, let's do minus. Now I understand that next week you are going to look at this and just write the answer, but now let's just separate these and use the property because this example is there to illustrate a property. So I'm going to take the derivative of x cubed separately, plus 5 times the derivative, remember, kick the constant out, that was the last property, the derivative of x, and then minus the derivative of x to the 7 halves. So I have 3 separate functions that are added or subtracted, therefore 3 separate derivatives, preserving the signs in between. The derivative of x cubed is 3x squared. We know that by the formula we covered earlier. You drop the power down and you subtract 1. That's all it is. So please don't make it difficult. Plus 5 times the derivative of x is 1. Very good. So I'll write times 1 minus, drop the exponent, x, and then subtract 1. So what's the answer? It's 3x squared plus 5 minus 7 square root of x to the 5 over 2. And as I said, it's fine to go from here directly into the answer starting next Saturday. You have a week to enjoy 10,000 homework examples and then go right into this. So let me see if we can find some interesting examples from the textbook. I did all of this, I did all of that. That's all done. That's left. All right, so I just want to give you one example from the textbook. So this is what you would find on your homework. This is example problem 22. I'll give you about 17 seconds. It's f of t is equal to 6 root t minus 4t cubed plus 9. So find f prime of t, the derivative. And we'll discuss notation right after this example. Proper notation, so you don't trigger my allergies and stuff. All done? So the derivative is what? We have square root, that's going to be 1/2. So half of 6 is 3. T, 1 minus 1/2 is negative 1/2. Minus 4 times 3t squared plus 0. So the derivative, as the final answer, is 3 divided by square root of t minus 12t squared. Are we all good on this? It should take a whole page if you want to do the limit. Have fun. So the trade-off is you are memorizing these shortcuts to make your lives much easier. That's what we are doing now. Just like multiplication table, so you don't have to go and add forever. Like 9 times 8. Yeah, it's going to take some time. All right. The next one, next big formula, is that the derivative of e to the x is e to the x. Cool, right? Obviously, only one function under the sun should be able to do this, and that's this winner here. So, derivative of e to the x is e to the x. Awesome. Is there more to it? Sure. Later on, there's going to be much more on it, but for now, that's it. Now let's talk notation. It's important to learn notation so that you can communicate your ideas and your knowledge. Mathematics is very particular because it is the only universal language in the galaxy, okay? Many of us over here will speak a different language or attempt to speak a different language, but we all agree when we see 2 plus 2, we know it's 4. And that's like that in every country on the planet. So now, when you are dealing with this, you remember how earlier I told you never dare writing VA equals 7? Because that has no meaning. VA equals 7 is not an equation at all. It's just nothing. You have to write VA, and then you can say, maybe 2 dots or whatever, and you say x equals 7. Because x equals 7 is the vertical line through 7 on x-axis. So x equals 7 is equation, VA equals 7 is nothing. Also, another big deal that aggravates a lot of people, myself included, is writing limit equals to 7. That's also meaningless statement because you cannot write LIM without function following that. LIM on its own is meaningless term, just like SI, well, actually SIN, that's a sin, it's a religious term, but COS, right? You can't write and just walk away, right? It's, what do you mean, COS? It has to have an argument following. It has to have something in that box. So notation is extremely important in mathematics. You can't do that with ln. You can't do that with limit. You can't do that, right? So now, when we are talking about notation for the derivative, we understand that we can write if f of x is equal to x squared, the derivative of f of x is 2x. So this would be a pair, and I'm going to box this as a pair. Note that I had to start new expression, right? You cannot write x squared equals 2x. It's not, right? X squared is the, we had them in a previous lecture, completely two different functions. So you have to read it to yourself, right? Function is x squared, the derivative of that function is 2x, right? So it's a completely two different separate things. You can also say y is x squared. Sure, we also have dy dx notation and as a derivative, and it's going to be 2x. Again, a completely separate expression which says derivative is. The first one is close to Newton's notation. Newton used to put a dot above the function to denote derivative. And you will still find mechanical engineers who do that. When I took statics and dynamics, professor who taught those courses used dot notation above theta and velocities and so on to show into acceleration and so on. So the Newton's notation from a single dot and then two dots for two derivatives and so on moved into these primes. So that's a Newton's notation. This is a Leibniz notation with a dy dx, which is far superior to Newton's, and I'll explain why as we move along to the course. But you have that as well as a way to denote derivative. So function, and then separately, next line on the side, I don't care where, but you can't put equal in between. They're separate expressions. Now, you might want to go in line, and there is a way. You can't use this anymore, but now what you can say is the derivative of x squared is 2x. Now, this is the only way to write the derivative in line. So this is the only way where you can actually have function and derivative show up in the same expression. Otherwise, differential equations. So you have these two methods where functions go on a pile, derivatives go on a pile, or what we call linear writing, where you say the derivative of this function is 2x, right? But you start with the derivative. Now note that there is no y here, like there is there, because that's the y, right? See? Y is x squared. So think of this. Peel it off, pull it on the side, right? Peel it off, pull it on the side, replace it with what it is, and then you can just say the derivative of y off. Word for multiplication, right? It's d over dx, which is a derivative operator. Later, you'll learn about those things. So derivative operator, ddx, so derivative of multiplication. Derivative of whatever the function is, and then you put the derivative there. So those are the notations, and they're very important so that you don't get in trouble later with someone not understanding what you want to say. And you saw me carefully exercise that all the time. Observe that in this particular example, the book is giving you the function and is asking you to find the derivative. Now, can you rewrite this and just go d dt, put these brackets, put all of this in, and write that? Yeah, you can. But, I wanted to show also this particular way of writing. So now you have inline derivatives, right? Linear writing, and you have these where you state what the function is, and then you restart writing the derivative is equal to, and so on. So just don't put equal in between them. We have one more concept. and that is higher derivatives. And we're done with this section. Wasn't that much. You have to memorize 6 formulas, notation. 6 formulas and notation, that's all in this section. So what do we have with the higher order derivatives? Well, we have a second derivative, and then the third derivative, and then the fourth derivative, and then the fifth derivative, and then the sixth derivative, and then the seventh derivative. You get the idea, right? Higher order derivative will just be the next derivative in line. What's a third derivative? Third derivative is the first derivative of the second derivative. What's a 78th derivative? It's the first derivative of the 77th derivative. So in order to calculate some of these late derivatives, you have to calculate every single one before you had that one. There are no shortcuts in, well, there are a few, right? What's a 154th derivative of e to the x? There we go. That's easy, right? What's a 104th derivative of x squared?
Nothing.
0. Because x squared, it goes into 2x, and then goes into 2, and then it goes into 0, and then all of the response is 0, right? So as long as the order of the derivative is higher and then the power of the polynomial, it's going to die. E to the x will always stay to the x. And you will see that sine and cosine are going to loop. The rest, you have to grind through. Now, why do we have higher order derivatives? Because of the world. All right? You have the position, but you also at one point want to go home, right? Well, there is a position function, right, to get you there. And what's the derivative of the position? Change of distance over change in time is miles per hour is it's velocity, right? It's velocity. And what's the change of velocity? Acceleration. And what's change of acceleration? Jerk. Very good. So, didn't we just go 3 derivatives down the line? And the answer is yeah, we did. Because when you start with the position, which is measured in miles, away from home, you say, take the derivative in respect to time of that position, and you will get velocity. Why? Because you get miles per hour. Right? Velocity. It's change in position, ds, over dt. Change of position and time. That's a derivative. And now, what do you do when you change? How do you change velocity? You push on the gas pedal, right? You push the gas pedal, you go from 30 to 70, right? So acceleration is going to be change in velocity, but velocity was change in position, so you see how acceleration is the second derivative of position. We are going to have a detailed lecture on this, but I just want to say that the higher derivatives is not that, you know, something that mathematicians say, oh, look, this would be cool to annoy students with, right? It's a necessity. Physics, engineering uses this stuff. Economics as well. When we start talking about concavity of the graph, it's a second derivative to understand investments better. So it's needed, right? So now, what do I have? Without continuing this story, there is another 3 lines that I need to write underneath this, which will be in its own lecture. So what's happening with these derivatives? Well, I'll write this. So, fourth derivative is a first derivative of the third derivative. That's what it is. Derivative. So let's take a look at, say, function is given as x to the 8 plus 5x to the 7th, no, 5x to the 3rd minus 4x plus 9. And let's take all of the derivatives until we hit 0. I'm going to regret that as x to the 8. I'm going to regret that very fast. The first derivative, we can mark it as a prime. I could always cheat and put that 8 to a smaller power. But just because I didn't think about it soon enough, let's hate it all the way. This is the reason why I don't watch it back, the lecture. Because I will be going, it's like, come on, really, x to the 8? But hey, we have the first derivative, easy, right? Let's regret next one. 7 times 8 is? Yes, x to the, nice, plus 30x. Awesome. Minus 0, but we don't care, right? Now, third derivative, 3 primes. Ooh. Yes, so we're going to multiply 156 by 3 first, right? Which will give us 168. And then double that. 330? No? 336. X to the 5 plus 30. The derivative of x is 1. On to the next problem. Now look, the derivative notation changes now into parentheses with a number which states the order of the derivative. And from here on, we will always use the numbers. So you have a prime, double prime, triple prime, and then after that, put the number in the parentheses and keep going. So the general notation is this, actually. And you will see it in your later courses. Calc 2, Calc 3, differential equations, they all have this notation popping up here and there. So higher order derivatives are denoted like that. All right, so fourth derivative, times 5. 1500 and 1830, because it's 1830. X to the 4. All right, awesome. Let's cry more.
This is how you kill 5 hours of calculus.
Exactly. We just do this and then we go home. Technically arithmetic, right? Yeah. We're just learning, hey, we know how to multiply. Okay, we're going to double this number twice because we are multiplying by 4. Double it twice. No calculators here. So we have 3660. So 72, 7320. X to the 3. Now, you could double this and add it to itself. That's another way to do this. 14,640 plus this is 21,960. Are we all good on that? Oh, you didn't get to your calculator in time?
No, we messed up our math for 336 times 5. No,
Why not? It's 15 and then 15 and 30. Ooh. Ooh, 1680.
That's my bad. And this is why you can't watch the video.
Yeah.
And this is why I always use a calculator on test. Common preference will do simple arithmetic and let the calculator does it.
All right, so double. We have 3360, 6720, and then 13440 with 6720 is 20160. Is that good?
Yeah, it's just big.
Nah. And then double this, that's easy. 4, 0, 3, 2, 0. The eighth derivative is going to be just the number because x is equal to 1. I mean exponent of x is equal to 1. And there it is on the ninth derivative. We are hitting the 0. And then all of the next derivatives, right? Every single one of these is going to be 0 thereafter. That's technically all I have to say for these derivatives. Now we are going to have a separate lecture on what is the purpose of the second derivatives. We're going to have a separate lecture on the concavity and stuff. We're going to have a lecture on velocities and application of this stuff. So there is going to be some understanding of these derivatives as we go along. The purpose of this part here is just to understand that in order to find the fifth derivative, you have to have the fourth one, and then you just take the derivative of the fourth to get the fifth. Take the derivative of the fifth to get the sixth, and so on. Which concludes the lecture on 3.3, rules of differentiation, where we just learned these vanilla rules for the most basic functions. And we've also seen that the properties, right, you can kick the constant in front of the derivative, and you can take the sum and difference of functions and take those derivatives separately from each other. So the next one is on product and quotient rule. So we'll restart the stream for that, the new title and everything. Bye, stream.